Thank you very much, Praveen, for the introduction. And if you are maths nervous, don't worry, there won't be a single equation in this talk. In the short film that we just saw, there were two crucial aspects about climate change and tipping points. The first one was about time scales. Someone in the movie said, the swell used to be like music in our ears, but now it's threatening the survival of our grandchildren. So sea level rise is something that is a slow process. You don't see sea level rising from one year to the next, but over the course of a generation and a lifetime, it can have a devastating consequence, and it can be an existential change. The other crucial thing about the climate is that some parts of it are irreversible. So someone else in the movie said a lot of people lost everything. There are some changes that cannot easily be undone. And once they happen, you need to put a lot of effort and need to go a long way to go back to where we came from. So when we talk about timescales and irreversibility, abrupt changes in the climate are now known more under the term tipping points. But what is a tipping point? So I brought this bottle here to illustrate what this is. So this bottle has, well, let me first say what a tipping point is in general and then get to the bottle. So a tipping point is a critical threshold beyond which a system can undergo rapid and irreversible self-perpetuating change. So we had the rapid and the irreversible, and another feature is the self-perpetuative nature. So with this bottle here, this is a bottle that has two stable states. It can be stable in the upright state, and if I tilt it a little bit, it will go back to where it came from, right? But if I tilt it a bit too much, there will be a point where the bottle tips. So right about here is the tipping point. And the difference between this stable state and the stable state down here, or how to get from one to the other, is that at the tipping point, you shift from a negative feedback to a positive feedback. So a negative feedback is a force that pulls you back to where you came from, so it counteracts the perturbation that you're putting on the bottle. But if you tilt the bottle too much, at some point, gravity actually wants to pull in the direction where you push the bottle. So this is a positive feedback where you have a self-perpetuating motion, and you will, there's no way to stop the bottle here until it falls. So this is the idea of a tipping point. And the Earth system is full of positive feedbacks as well, of course also negative feedbacks. But the fact that there are positive feedbacks means that also in the Earth system, there are the so-called climate tipping elements. And this map just shows some of the most discussed global ones. And I want to focus on three just to exemplify how they come about. So the first are the ice masses, the ice sheets at the poles and in Antarctica and in Greenland. So in Greenland, for example, the ice is 4 kilometers thick, which means that up there it's really cold, much colder than at the surface. And in a glacier, as we see here on this figure, we have a region up here where it's cool, where the glacier gains more mass than it loses because it doesn't melt much, but you have snowfall which accumulates on the glacier. Below this line, which is the equilibrium line, you lose more mass than you gain because you don't have so much snowfall anymore and you have more melting because it's warmer down here. So if you now imagine that a glacier retreats because it's melting, then this area here, which is in the net gain area, will become smaller and smaller compared to the net loss area, which means that you have a net loss in total and the glacier melts even more. So you have a positive feedback which accelerates itself until the glacier is completely gone. So this is how positive feedback in the ice caps could lead to a rapid retreat of the glacier. Now, ice sheets change over thousands of years, so this is a very slow tipping point. There's also a faster tipping point in the biosphere, which is the Amazon rainforest. And the Amazon rainforest is an example of moisture recycling. So the trees in the Amazon, they evaporate water, and this water forms as clouds and rains back down on the rainforest. So a lot of the rain that keeps the Amazon alive is actually recycled water from the forest. Now, if you cut down a lot of trees because of deforestation, for example, then you have less water that evaporates and also less rain. So this could increase tree mortality also in a feedback loop, which could then shift the rainforest to a savanna state. And whether the Amazon rainforest is actually close to such a tipping point is something that is very actively debated in the literature. And the third tipping point I want to talk about today, or the third tipping element, is the Atlantic meridional overturning circulation. And this is what I am focusing on in my PhD. So this is what we'll spend most time on. And so this is a long name for a big ocean current. So this very cool map here shows the currents of the ocean at the surface, where we have the velocity shown, so the speed, and the color tells us how warm the water is. So you see that it's warm at the tropics and then gets colder below. And one thing we see here in the Atlantic is that there's a long stream from the Gulf of Mexico here all the way to Europe of a strong current that brings warm water here to the north. So this part here is the Gulf Stream, as you may know, but this is actually a much larger current system that goes all the way through the Atlantic and is that's why it's called an overturning circulation, because it brings water all the way. And it kind of acts as the heat pump for Europe, because this warm, salty water is transported all the way here. You can see that it's still green up here. And this heat gets released to the atmosphere. Also, a lot of moisture gets released to the atmosphere, which then gives us the very mild temperatures that we have here, and also the lovely British rainfall that we all love so much. And if you would think about what the climate would look like here if we didn't have the AMOC, then you just have to look on the other side of the Atlantic in Newfoundland, where we are at the same latitude, even in Alaska, but the weather, the climate is significantly colder than here. Now, the idea that this AMOC could at some point be gone has also been picked up by the movie The Day After Tomorrow. And here's this very dramatic image where Big Ben is completely frozen. Now, of course, this is not a scientific movie. There is a lot that is exaggerated and wrong, but it's not pure fiction, the idea that the AMOC could shut down. And the reason for this, as you might imagine, is that there's also a positive feedback in the AMOC. So here we see the water flowing northward, warm and salty water, and as it gets north, it cools. And so then you have cool and salty water, which is very heavy and sinks down near Greenland and in the high latitudes. And then after it has sunk, it flows back as a deep current and then resurfaces in the southern Atlantic and begins the overturning journey again. So this sinking water, due to the cold and salty water, is basically the pump of the AMOC. This is what drives the current. And there is now a concern because this pump might be under pressure. The reason is that we currently have a lot of fresh water entering the North Atlantic, and fresh water is much lighter than salty water. And this fresh water is coming to some extent from Greenland melting, from ice falling into the water, also from sea ice melting, but also from changes in rainfall patterns in the North Atlantic due to climate change. And so if you have this fresh water put into the North Atlantic, you might stop this pump that keeps the currents going because you are replacing the heavy salty water with the fresh water. So this is a depiction of the positive feedback loop that is at play here. If we have fresh water coming in, this reduces the sinking, the strength of the pump, which then leads to a weaker overturning circulation overall, which will transport less salt from the tropics to the north. So that makes it even weaker, and you then start looping in this loop until, hypothetically, the whole current system could shut down, or at least go into a very weak flow state. Now, the idea that the AMOC could be multi-stable, so that it could have more than one stable state, just like this bottle, goes back already to the year 1961, where an oceanographer called Henry Stommel came up with a very simple model. He just kind of described the northern Atlantic by one box, one container of water, and the tropical Atlantic by another box. And this is then warm and salty here, and cold and fresh in the north. And there are tubes that connect the two bottles, and the flow between the two boxes then depends on the salt and temperature difference between these boxes. And what he found with this model is that indeed, if you put fresh water into this northern box here, you get a region where you have two stable states. So as shown in this bifurcation diagram here, let's start here at this point where we are today. If we now increase the freshwater input, then the stable state of the AMOC will follow this red line. So it will weaken a bit, but it will kind of stay in a relatively strong state. But then comes this critical point right here, where we lose this stable branch and we fall off to the collapsed state. And now you can see that this change would also be irreversible. So once you move down to this other stable state, you would have to reduce the freshwater input all the way here until this unstable collapsed state disappears, and then you would recover the AMOC. So this means that once you have crossed here, you cannot just simply go back to come to today's state. Now, of course, we know a lot more today than since 1961. And one line of evidence we have is from looking back into the past. So if you look in Greenland, where the ice, as I mentioned, is 4 kilometers thick, you can drill down ice cores and then recover basically a time machine of the past. So the way how this works is that the ice accumulated year after year on this glacier. And so if you drill down, you will get to older and older ice. And in this ice, you still have air bubbles that haven't been touched since the time when the snow fell. And you still have the same chemical concentration of the air in these bubbles as thousands of years ago. So by very carefully extracting this ice core and measuring the air bubbles in there, you can reconstruct the temperature of the last 100,000 years. And this is the result. So in this graph here, this is today, and we're going back in time, so down the ice core up to 100,000 years. And what is shown here is the temperature anomaly relative to the last century. So you see that the temperature in Greenland has not been constant at all over the last 100,000 years. There have actually been very massive and sudden shifts, for example here, of up to 15 degrees Celsius, which occurred within 150 years or so. And the best evidence we have is that these abrupt shifts are because the AMOC reorganized, because it changed between different stable flow states and therefore brought more heat and less heat alternatively to Greenland and the Northern Hemisphere. Now, about 11,000 years ago, so this is here, we exited the last ice age and had this very stable climate, which allowed us to begin farming and to grow the civilizations that we have today. So this has been a very exceptional climate compared to the past 100,000 years. And then in the last 150 years or so, we started to put a lot of greenhouse gases, so carbon dioxide and other chemicals, into the air, which has led to quite a rapid warming already on this time scale. So the red line here shows how much the northern hemisphere or the Arctic has warmed already. And this cross up here shows where we are predicted to end up in 2050. So we see that we are really entering uncharted territory with the climate change we are seeing right now. Now, of course, if we see these big changes in the Arctic, we want to know what does this mean for the AMOC. And we would like to predict what will happen in the future, but of course, unfortunately, we don't have data of the future. So the best thing we can do is to look at climate models. And we already know one climate model, which is the simple box model by Henry Stommel. So in physics, we sometimes speak of this as a spherical cow. You know, if you want to make a model of a cow, you can start by just drawing a circle, putting some black patches, and it says moo. That's not a great model of a cow, but at least some simple description. Now, you can, of course, do a bit more. If you add more pixels or more boxes, then you can actually resolve the shape of the cow a bit. You can add legs to it, and you can also add colors to make the cow look a bit more like a cow. And the same happens with climate models as well. And then, of course, you can increase the resolution more and more. So you divide the Earth into more and more boxes, or the cow into more and more pixels, and then you get a more realistic and more detailed description of the system you are trying to model. And in each of these little boxes, you then have variables, which are the colors essentially, like the temperature, the pressure, how many clouds there are, how much it rains or not. These are all variables in each grid box. And then the boxes talk with each other, and that gives you the wind speed and the ocean currents. So the air and the water moving between the boxes. All of that put into mathematical equations and making them work on huge supercomputers. And the result is actually pretty good. This is just showing now a climate model used for weather prediction, so on short timescales, just so we can compare. On the left side, we have a video from satellite observations, and on the right, we have a simulation by a global climate model. And you see that there's a remarkable similarity in the features of the clouds, and that the model really captures a lot of what's going on. So you see here, for example, the big thunderstorm clouds in the tropics, and then you also see the low pressure systems moving along here, just like you see it here. So we are able to simulate the climate, or at least the weather and the climate very well, just by solving equations on huge supercomputers. But there is one problem. If you take a big model like this, let's say you have 100 boxes along the equator and then 100 boxes from south to north, and 50 levels, 50 layers for the atmosphere and 50 for the ocean. That gives you 1 million boxes. And it means you have to solve these equations at 1 million points at each step in time that you're running your model. So this is computationally very heavy, and you need a long time even to run those simulations, and it requires huge amounts of energy and resources. So you cannot actually run them as much as you like and look too far into the future, at least with these super complex models. And if you want to know more and run them more, you have to revert back to the simpler models, maybe not the spherical cow, but something in between. What you can do with these models, however, is to look at the next like 100 years, so until the end of this century. This is a lot of these complex models are run for this time period, and the results are always summarized in the IPCC report. So the IPCC is the Intergovernmental Panel on Climate Change, which takes all the studies from recent years and puts them into a gigantic report. And here we see how the AMOC is expected to evolve until the end of the century. So the brown here just shows simulations of the past, and you see that the AMOC has been relatively stable. And then from here on, we have future predictions for two scenarios. On the left side here in blue, we have a low emission, so the idea that we take strong climate action and therefore don't emit so many more greenhouse gases. And on the right-hand side, we have a high emission scenario, so the idea that we don't do much about climate change. And you see that in both cases, the AMOC weakens, but it weakens a lot more for the case of high emissions. You also see that there is quite a big uncertainty on how much it will weaken, as shown by these shaded regions here. So this experiment was done in a lot of different models, and the shaded area just shows you how different these models were in their predictions. So even though there's quite a lot of uncertainty, we are relatively certain that the AMOC will weaken until the end of this century. This is also what the IPCC concludes. The AMOC will very likely weaken over the 21st century. We are quite confident about that, although a collapse is very unlikely. Medium confidence, we are not so sure about that. Nevertheless, it is a physically plausible scenario. And then the report also says that such a weakening would strongly impact natural and human systems. So what would it actually mean if the AMOC would tip? How would it change our climate? And we can also look at this question with climate models by artificially turning off the AMOC and then seeing how temperatures around the world change. So here a climate model was taken and it just shut off the AMOC. And we see here in colors the temperature difference relative to today. And one thing you see is that you get cooling in the northern hemisphere almost everywhere, and quite a lot of cooling also in the UK. So this is more than 2.4 degrees, and if you read the paper, it goes up to 8 degrees Celsius of cooling compared to what we have today. Now, of course, this is just a kind of not a realistic experiment, because we are just shutting off the AMOC without having any global warming due to greenhouse gas emissions. So if you kind of add the global warming on top of the shutdown of the AMOC, then you get this result. So you see that the whole planet warms, except for the UK, basically. So except for this region in the North Atlantic, which includes Scandinavia and the UK. And so now you might say, okay, that is great because we have global warming and now we have a competing effect and this will kind of balance each other out. But unfortunately, it's not that simple in a complex system like the climate. You can't just add two effects and the sum will be the result. Because one thing you see here is that if it gets colder here and warmer here, you have a very large temperature gradient, so a strong temperature difference as you go from north to south here, which gives you a lot of energy for severe storms and other extreme events. So this is, for example, one impact that you could see as a result of AMOC collapse plus global warming. And to look a bit more at the UK, there's one study which looked at the impact on agriculture. And so here we see the temperatures, average temperatures in the UK 4 years ago, in the year 2020. And now they analyzed predictions of the temperature for no collapse. So the AMOC survives, but we have global warming, in which case you see that all of the UK gets warmer in the year 2080. So I will be 84 years old then. And in the case where you do have an AMOC collapse, the UK actually gets colder than it is today. But it's not only the temperatures that change, it's also the rainfall. And the study found that if you have a collapse of the AMOC, then you have large regions here in England, as shown in this red area, where you have a strong water deficit. So without actually irrigating artificially, this land would be too dry to farm crops, and you would have to turn it into grassland. So if the AMOC would tip, at least according to this study, this could have quite massive impacts on the UK economy and on the lives here. But of course, the AMOC tipping is not only a UK problem. You would also have expected sea level rise in the Atlantic basin, because changing the ocean currents also changes where the water goes. You have more severe winter storms predicted over Europe because of this temperature difference that I mentioned. And overall, the whole tropical rainfall belts would shift south, which means that some regions that used to have rain would suddenly have drought, and those which had moderate rain would suddenly have a lot more rain. So you can have droughts and flooding in the tropics as a result of an AMOC collapse. So all of this sounds pretty horrible, I would say, and therefore it's even more important that we know, well, is the AMOC tipping or not, right? Are we approaching a tipping point? And well, if you read The Guardian, you would know that yes, we are, and it's happening next year, right? The Guardian wrote an article last year that said the Gulf Stream could collapse as early as 2025. And this was not only The Guardian, this was picked up by a lot of news media saying that we might have our real day after tomorrow very soon. And all of these news headlines didn't come from nowhere. They are based on a study published in Nature Communications, which was entitled Warning of a Forthcoming Collapse of the Atlantic Meridional Overturning Circulation. And I would just like to use this example and dive a bit into it, because it explains quite well how you get from the scientific publication to the news headlines that you would read in The Guardian or on BBC. So the idea is that we want to predict the point of reaching the tipping point from observations that we have. We don't have a lot of observations because we only started to actually measure the currents of the ocean 20 years ago. But we have a bit more of data by looking at the sea surface temperatures in the North Atlantic. You can use that like a detective as a fingerprint of the AMOC. So here we have a stronger AMOC, up and down is a weaker AMOC. And this is reconstructed for the last 150 years. So this is the data that we have and that this study has. And now we're supposed to say, as mathematicians, are we approaching a tipping point? And if so, when? So I don't know, maybe raise your hand if you think we are approaching a tipping point based on this. Okay, a few people have very good eyes. Who thinks we're not approaching a tipping point based on this data? All right, so we have about 50-50, but then we have a large group of people who find this data insufficient to determine whether we are close to a tipping or not. So yeah, the question is this just going to continue, or are we going to tip down abruptly? We cannot see this from this figure, but we can be a bit smarter and use some maths to extract a bit more information. And the idea is that you view the system. So now we imagine we have a bistable system like the bottle, or an AMOC having a strong state and a weak state. You can view such a system in terms of a stability landscape. So here we have the stability increasing as you go down. And you can imagine the system like this, a landscape with two valleys, and your state is now this ball rolling around. So if we take again the example of the bottle, This minimum here is a stable point. If you put the ball there, it won't roll anywhere. But if you cross this hill here, this hill is a tipping point, and if you cross it, you will roll over to this other stable state, which is the other valley here, right? So we kind of have the stability landscape as a function of the tilt angle of the bottle. And of course, now you could also imagine that this stability landscape changes. For the bottle, for example, if I would drink a bit more water, its stability properties would change. And for the AMOC, it's climate change that is changing. And so if the landscape is changing, then these valleys also change. And for example, this valley could become a bit less steep. And if you would now imagine a ball rolling around in this valley, and you would poke it a bit and shake it around, then it would have an easier time moving around in this flatter valley than in this valley, right? It would more easily also tip over. I prepared a little simulation to show this for the little spherical cow box model of the AMOC. So here we have the stability landscape of this box model, and here we have the stability diagram. So here's the stable on state, the stable strong AMOC, and here's the stable collapsed AMOC. And now we will slowly increase the freshwater forcing while wiggling around the Earth a bit. So let's see what happens. So you see that as we increase the freshwater forcing, we are changing the stability landscape here. This valley becomes shallower and the tipping point gets closer. And now as we are moving along this branch, at some point this valley disappears altogether and boom, we tipped down to the collapsed AMOC state. So this would be an example where because of climate change, or in this case freshwater forcing, you're shifting the stability landscape and then you have a tipping. And this is now for the very simple model, but if you run experiments with more complicated climate models, you see that they show a very similar pattern when you increase the fresh water in them and decrease them again. So you also have a strong evidence that you have this actual collapse of the strong branch here at some freshwater value. Now you might look here and look at the wiggles, and I don't know if to you it looks like they are getting a bit bigger or not, but this is essentially what you do now in the statistical analysis. You look at the wiggles along here. So this is the time series I showed you earlier from the past 150 years. And then you see if the wiggles are getting stronger or not. And based on the size of the wiggles, you analyze the stability of this landscape. And so this is the result from the study that said that the Gulf Stream could collapse by 2025. So in blue, you see the stability of this valley of the landscape. And you see that after about 1920, it starts to decline. So the wiggles are getting bigger, and from this you deduce that the stability is decreasing. Now the author said, okay, well, let's just draw a line through this. We have a decrease here, and we know that the tipping point is when this decrease hits zero. So if we just fit a line, we can see where the tipping point would be by seeing where it hits zero. And the study found that it hits zero in the year 2057. But of course, there is a lot of uncertainty in this statistical procedure. So this is not an exact result. Instead, this is just the most probable value. And then what you usually do is you define a confidence interval. So you say that within a certain range, I am 95% sure that this is where the tipping point is going to be. So this is the uncertainty interval for this study. And we see that it ranges from 2025 all the way to 2095. This is also what they state in the paper. And then the news headlines just took the lower bound of this confidence interval because that's the most dramatic result, right? And said, oh, the AMOC could tip in 2025. But even according to this study, the probability that it would tip that early is very low. It's just the lower bound of where you are 95% sure that it would happen. But it gets even a bit worse because there's even an uncertainty to this confidence interval. Even this uncertainty shown here is not the full picture. And this is because in climate modeling or in climate research, like in any other research, there are several sources of uncertainty. The first uncertainty comes from the limitations of data, right? I mentioned that we don't really have direct observations of the ocean currents for more than 20 years. And before that, we have to be detectives and deduce how the AMOC might have been by looking at sea surface temperatures or by looking at ice cores. So by doing these methods, we make a lot of assumptions that add up to the uncertainties in our results. The second category of uncertainty is the modeling uncertainty. So we have to make a lot of assumptions when modeling because we cannot build the perfect model that resolves everything. As I mentioned, the super complicated models are very expensive computationally to run, and you cannot run them for thousands of years, only for a few hundred maybe. So then you have to revert to simpler models, which require less computation, but you also have to put more and more assumptions into the processes that you're not actually resolving. Now, these two aspects you could, in principle, solve by just having more data and better models, right? But there is a third category of uncertainty, which is the chaotic nature and the complexity of the Earth system itself. And that's something intrinsic that won't change. I don't know if you know anything about chaos theory, but it's the idea that someone once said, if you have the wing of a butterfly flapping, that could change whether there's a tornado next week or not. So small changes in the state of the system can lead to very different outcomes in the end result, which makes it super difficult to predict things long in advance. We see this, for example, with weather prediction, right? We have fairly good weather predictions for up to 2 weeks or so, but after that, the chaotic nature of the climate and the weather just makes it impossible to say whether it's going to rain or not 5 weeks from now or 20 weeks from now. Of course, with climate, we can say a bit more because in climate, we are not interested in whether it will rain 28 years on the 2nd of February in Reading, but we are more interested in averages. What will the average temperature be in Reading in 25 years, right? But I just wanted to show one example from a climate simulation that I've been running, which shows the AMOC strength here for 100 years, starting out close to the tipping point actually, and just changing the state a little bit. And you see that they are a bit different, but they generally follow the same path. So you could say, oh, okay, we're in the same regime, and we can predict what's happening fairly well. But then if you actually run the simulation for longer, you see that one of them, or at least at first both of them, increase in the AMOC strength, but then one collapses while the other one goes back to today's state. So this is kind of chaos playing out in a real climate model, that even if you have only a slight change in your initial conditions of the model, you can have a very different outcome, and that makes it very difficult to predict. So in our research, we try to understand the limitations of this predictability a bit more by actually looking at the stability landscape and going a bit beyond just a schematic. We want to know, what does the stability landscape of the AMOC or of the Earth system actually look like in these climate models? And I've just shown an illustration here. So this is not a real landscape, but it's just, again, the idea that you have two valleys corresponding to the two different stable AMOC states. And if we understand this landscape better and where we are in this landscape, we can maybe see a bit more clearly how close we are to the tipping point and whether we are on a route to go to the other state or whether we are actually on a route to return to the AMOC state that we have or had. And what we find is that this landscape is actually a lot more complicated than this picture. Especially if you get close to the tipping point, it's a bit more like a maze where you have channels that lead you to one state or the other, and it generally becomes a very fuzzy region, which makes it really difficult to say where this tipping point actually is and how strong you would have to force the climate to cross this tipping point. So now, you probably came here to know actually how close we are to this tipping point and how bad things are going to get, but I just spent half an hour telling you, well, we don't really know, and we also might maybe asking the question of when the tipping point will be crossed is not such a sensible question. So what do we do with this, and how do we move on? What do we take home from this? One viewpoint would be that, well, there isn't really a sign of tipping if you look at climate change so far. This figure is also from the IPCC, from this big report on the current state of climate change, which shows that if you increase greenhouse gas emissions, so this is the cumulative emissions of CO2 here, how much warmer the world is going to end up getting. And you see that this is pretty much a straight line, which suggests that if you put a little bit more CO2 in, it's going to get a little bit warmer. That it's proportional how much we put in and how warm the climate is going to get. So this would suggest no sign of tipping points. But this is, of course, only looking until the year 2050, actually. And so we are not looking very far into the future. This is also looking at global mean temperature, so the whole average across the whole Earth. And I just wanted to go back to this idea of how temperatures changed in the past in the Arctic. And you see that this is not linear at all, our Earth system. And currently, we are really pushing the climate in an unprecedented way. So I don't think that this linear picture is very promising if we look beyond 2050. And this suggests that there can be a lot more complex behaviors and surprises in the climate system than just a linear increase of global mean temperature by increasing CO2. Now, yes, this is also then what the IPCC concludes. Abrupt responses and tipping points of the climate system cannot be ruled out. High confidence. So this high confidence is basically IPCC lingo, which says we are pretty sure that we don't know. So there's a lot still to be found out. Now, of course, if you're a policymaker, you would like to have a number, right? You want to know in which year are we going to cross the tipping point if we don't stop emitting greenhouse gases? Or at which level of global warming or CO2 concentration are we going to cross the tipping point? But what I'm trying to say with this lecture is that we actually have too much uncertainty to determine such a point specifically. Due to the chaotic nature of the climate, we will maybe never be able to say with certainty this is going to be the critical threshold that separates us between a tipped AMOC and a non-tipped AMOC. It's a bit more that we have to speak in probabilities. I think about it a bit like a game of climate roulette, if you so wish. So imagine a scenario with low greenhouse gas emissions depicted by this bullet chamber here with one bullet. So there's still a probability that the AMOC could tip, or that any other tipping point could be triggered, but the probability is relatively low. We still don't have any certainty whether the tipping will actually happen or not. Now, if we compare this with the case of high greenhouse gas emissions in the future, we still don't have certainty whether we will tip or not, but the probability increases, because what global warming is basically doing is that it's adding more bullets into the bullet chambers and increasing the probabilities of abrupt climate change. And so this illustration also shows that even though we don't have full certainty, we still have agency. It still matters what we do, right? It matters whether we are playing with this bullet chamber here or with this bullet chamber, because the probability is a lot higher here, which means that the risk of having uncontrolled climate change is a lot higher in this case. And I know this is a bit of a macabre analogy, perhaps, but it is also this serious, because the livelihoods of millions of people are at stake between these two figures. Well, let me just go back again once here. So even if we don't have complete certainty, there's still something that we can do in terms of risk management. Think, for example, of a house fire, right? We generally don't know whether our house is going to catch fire in 2 weeks or something. But even if we don't know the exact date of a house fire or the exact way how it's going to happen, we don't just put our head in the sand, we still do something. We take risk measures. So for example, we have fire brigades, we build our houses with fireproof materials, we make sure that our plugs have switches and everything, and we have fire detectors in the walls. So all of these are risk measures that help us deal with the uncertainty of an event which is maybe not super probable, but would have a very high impact if it were to happen. So when you listen to the news and hear about climate tipping points, it often seems a bit like a binary story. You know, either we have tipping points which would lead us into apocalypse, or we are fine because we didn't cross any tipping points. And I would like to say in the end that this is not, I think, the picture that we should have, and this is not how we should view tipping points. Because even if we don't have tipping points in the future, climate change is still one of the greatest threats of our time. And even if the AMOC gets weaker and doesn't tip but then comes back, that could still impact the climate over the next decades to come. So it's not really this binary 0 or 1. It's not everything is fine or the world is going down in apocalypse, but tipping points are dangerous because they increase the risk that we might not be able to adapt to the changes that we see. And this brings us back to the crucial role of timescales. I mentioned, for example, that the ice sheets as tipping elements, they tip on the course of thousands of years. And you might hear things like, oh, if Greenland melts completely, you have 7 meters of sea level rise. That is a really big number and means that most of the Netherlands would be flooded. But that is also going to happen if it happens over a very long time. So in principle, humans would be able to adapt to that, even though maybe the Netherlands would have to relocate. But what makes the AMOC a worrying tipping point is that if it would happen, the change would happen relatively fast. We are speaking more about decades, so 30, 40 years from the state we have now to a much weaker state, which would then come with all the changes in temperature and rainfall and winter storms. I think I will end there and leave the final verdict of how terrible it is up to you, or maybe in the questions. And I would just like to say that, of course, the path to this lecture would not have been possible with a lot of collaborators and people who have helped, and I am very thankful to all of these people listed here who have joined in this journey up the way to here. And if you're interested in a bit more, there's this QR code here which you can scan, which brings you to a website where we'll put up a reference list so you can read up and fact check what I said. And it will also provide a link to the recording once it's available. So thank you very much, and I'm happy to take questions.